Hi everyone. This is runway ready for A401 Spring 2025. We did Oleo Strut testing for an RC aircraft. I'm Adina Jan.
I'm Nicole Jessamine.
I'm Olivia DeFazio. Right, so brief rundown of our presentation. We have our introduction, our background of why we chose to do this experiment, our methodology, then we show our results, and then the conclusion. So a brief project introduction by Liv.
So our initial goal was to be able to use this data for a control system for a full-scale Oleo strut. But we've shifted our goal because an RC aircraft Oleo strut was a lot easier to, for one thing, get and also just be able to budget for it. But the RC scale comes with a spring system instead of the standard Oleo strut air and oil pressure. So therefore, our goal kind of shifted with that to be able to create a test to gather the displacement of an oleostrut based on varying terrains to be able to model how the oleostrut acts for use with the typical RC aircraft, like with use for our design book fly speed team. This can help us ensure that if using this landing gear system, we don't encounter any prop strikes and we can overall help reduce the strain on the landing gear and the plane itself. Our group mostly stayed on schedule during the semester, with testing occurring about a week late due to the oleostrut being delayed in shipping. And our budget was solely used for the Oleo strat provided through the ME department. Additional components were bought by the Runway Right team or supplied through scrap materials from the machine shop.
Okay, so going over the project background a little, we looked at work from previous 401 group testing that involved the suspension systems because our group also worked with a suspension system. We know that currently in commercial aircraft, there is a innovation of automated systems coming out, but the area is still underexplored. So we wanted to see how different terrains affect the Oleo strut displacement itself. And once we got that relationship, we would be able to model a control system, and that would not just be for a regular RC aircraft, but we can also upsize it to like any type of regular aircraft and also commercial and military. And why it matters is if we get this model, we will be able to implement or generalize it to a larger category of aircrafts themselves.
So the system that we're using, since it is basically a suspension system, can be modeled as a spring mass dampener system, with the mass being the basically weight of the aircraft, which can be using that term a lot, and that's modeled just by using the load frame. Um, we're going to use the force from the load frame to help calculate the K value, the spring constant value, for the initial conditions. And we're going to use the initial no load scenario to find the damping coefficient. And then we also calculate the strain to ensure that the strut isn't going to break based on the parameters that we input. So the idea is that the system could be used with you inputting in the terrain and the weight of the aircraft, and then it will model it based on a combination of a spring dampener system and Hooke's law, and be able to tell you if the Oleo strut has a high chance of being able to break if it's going to be close to its failure point, and how much it's going to displace so you can account for prop strikes.
So this is going to be our test setup. As you can see, the shaker table simulates the terrain through the oscilloscope, which allows us to enter a smooth, rough, and roughest terrain profile and is connected to a plate supporting the wheel of the strut to produce movement. The strut itself is held in place through a machine fixture to the load frame. The load frame acts as the aircraft weight during this experiment. We'll measure the displacement of the Oleo strut through a motion capture software, with each scenario repeated to ensure accurate results. Here is our design of experiments table, showing what we plan to use for smooth landing, a moderate landing zone, and a rough landing zone, respectively. The key variables are the force and displacement caused by the changed terrain. We chose a 75% displacement as our safety limit from observation, and the experiment was run first without any weight in the load frame to ensure that the shaker table and motion capture were working well.
All right, so going over our measurement techniques, we used a calibration system where we marked measurement points both on the Oleo strut and also attached a measuring scale on top of the shaker table so we could record the variation in the displacement accurately. And furthermore, in order to ensure accuracy, we looked at a online physics tracker system where we calibrated the system, put in a like an X and Y reference frame, and then used an auto tracker to um, see if we can detect the displacement of a certain point on the Oleo strut and get our displacement graphs out of it so that this could provide us with further accuracy. And then you can go into this YouTube link to see how we did that. Okay, so test equipment and standards. The load frame that we used was a standard Instron 5900, and it was calibrated with the Blue Hill system. We used the Blue Hill system to get all of our load graphs and stuff. The RC Oleo strut was ordered by JP Hobby. It was for a standard RC plane. Shaker table was a general model shop shaker table that was connected to an oscilloscope that was giving us our required waveforms. The wave generator function on the oscilloscope was used as you will see in the video after this presentation. We also used attachment points. So in order to connect the Oleo strut to the load frame itself, we needed some fixtures to be made. So as you can see on the right, we have our custom-made fixture that we attach to the Oleo strut so it can fully get fixed and properly working in the load frame itself.
Um, to describe how we were going to do our testing, so first we calibrated the shaker table and Oleo strut and the load frame and zeroed out the force of displacement using the Blue Hill system. The shaker table was also kind of calibrated to ensure that it starts at a neutral position. So we made sure that there wasn't too much force at any given point where it was starting the shaker table out at a wrong position, so we wouldn't accidentally bottom out the shaker table. The load frame was then run using the Blue system to achieve the desired aircraft weight. So we entered in the desired 20 and 35 newtons respectively, and we changed the weight of the aircraft, that desired value, by changing the displacement rate of the load frame. So having it be a very slow displacement rate, and we calculated how many oscillations we were going to have with it just at about the same exact load so that we wouldn't run into any issues with the shaker table affecting the load frame and causing us to not have accurate results by setting a target load. So instead of setting a target load, we set a target displacement and had that displacement rate be very slow so that we had enough time to work within. The shaker table was then activated with the oscilloscope, changing the wave type, amplitude, and gain for each of the 3 different terrain types. And we recorded the Oleo strut and run it through the motion caption software. And we also took key information from the force felt on the Oleo strut through using the load frame and seeing what it was saying that the output of the force was and taking into account what we had set the weight of the aircraft to be.
For the risk assessment, our main potential risks were projectiles from overexertion of the load frame. If we crushed anything, then it would have thrown shards right in our faces. That is a risk that we mitigated by standing as far back from the load frame as possible, wearing safety glasses, and limiting the amount of load to what we judged to be a safe, reasonable limit. Another possible risk was damage to the load frame, which again we mitigated by not putting too much strain on the load frame whenever we could manage it. We also had the risk of damage to the shaker table, which again we mitigated by not putting too much weight on the load on the shaker table from the load frame to prevent it from bottoming out. Moving on to our results. During the experiment, we tabulated key values in addition to the exported data for easy access, which all group members can use in analysis. The smooth, rough, and roughest terrain categories are shown here, with smooth being a sine wave and the other two being a ramp with different amplitudes and gains to simulate a more rocky terrain. The situations were chosen based on no loading, 20 newtons this year, which was this year's DBF plane weight, and 35 newtons as a maximum loading to avoid damaging the strut or the shaker table. Each situation was run for each of the three terrains. Here's our recorded displacement graphs from the software for situations 1, 2, and 3.
So we have the first case of no loading, where we had zero load, and the tracker helped us analyze the displacement of the Oleo strut. There was some uncertainty due to the movement of the video itself, but we were essentially able to capture the overall amplitude of the movement itself to get our displacement. So this is no loading. This is for 25 Newton weight on top of the Oleo strut to simulate a weight of the aircraft itself, and then we also wanted like a close to maximum weight, so we used a 35 Newton weight from the Instron to analyze it on, again, soft, medium, and harsher terrains.
A function code was made with the terrain variables of amplitude, gain, frequency, and type, and the aircraft weight as inputs, and the displacement and strain of the strut as outputs. An initial model was run to achieve the slightly damp but mostly linear relationship that was expected between the shaker table input and the strut displacement. The no loading case was used to calibrate the damping constant, and the forces that we got from the Blue Hill load frame system were averaged and used to find a spring constant. The system was then run with the 20 Newton weight, as a 35 Newton weight had significantly more inconsistent force values, but that was to be expected given that it was pushing the shaker table towards its limit. The code uses a for loop to iterate for the displacement based on all the terrain values. As you can see here, the other thing that the MATLAB code does is if it is above the strain value to the point where it will break the Oleo strut, it will do this initial graph and highlight the key points of displacement in red, so you'd be able to see what displacements or what terrain values are causing the Oleo strut to break. Here we have our results for the smooth terrain, and then the rough terrain and roughest terrain. As you can see, it operated best with the smooth terrain, so that it modeled the sine wave just best for the overall displacement. If you look at the rough terrain, we were able to overall show that the maximum values aligned with our experimental data. Same thing with the roughest terrain. However, the actual displacement graphs don't show it nearly as accurately, as we would like to see this as more of a square wave in the future. Then the uncertainty analysis was done first based on comparing the measured versus calculated average displacement values. The uncertainty for the measured values is primarily based on the motion capture by using the markings on the strut to figure out the percent error. The calculated uncertainty was done by figuring out what percentage of the calculation was based on that experimental data and what the percent error from the experimental data was. These values were then squared and then taken the square root of to figure out what the total error was, which is then used to normalize our error value to closer to 20%. Overall, scenario 3 was not used in the analysis much because the percent error was significantly higher than the other scenarios. But our difference between the calculated and measured values only came out to be 8.33% average error.
So for the conclusion, the initial conclusions resulted in the MATLAB code matching with the experimental data, which could be used for preliminary analysis when choosing a landing gear system. For the error analysis, the error is most likely due to the motion capture software because nothing is perfect. Additionally, in calibrating the load frame to move the displacement very slowly so we could work within the same force, there could be a lot of induced error there. There could also be some error from simplifying the Oleo strut system, given we did not initially expect to have a spring system. All the other issues were basically chalking up to human error. The implications of this experiment was we were just trying to collect some data so that we could work with this system moving forward. And moving forward, we're going to do more modeling and more MATLAB coding to create a digital twin and more accurately reflect the actual RC Oleo strut.
Yeah, and we would just like to thank Professor Hoover for helping us out with this project. He was of great help. He answered all of our questions. And then we also wanted to give an additional thanks to Lucas Monroe, who helped design and manufacture the fixtures used for the Oleo strut that went into the load frame itself.